Okay, this is Math 105, section 2.2a. Okay, so to graph a function f, we can just plot the points, right? X and f of x in a coordinate plane. Okay, remember f of x and y are the same thing. Okay, so when we say f of x, we're referring to y. Okay, so we're just plotting the points x, y, whose x coordinate is our input, and the y coordinate is the corresponding output of the function. Okay. So if f is a function with domain A, then the graph is the set of ordered pairs x, f of x. So the set of all x, y's, such that x is part of our domain. Okay. So in other words, the graph of f is just the set of all points x, y, such that y equals f of x, or that f is the graph of the equation. Okay. So we're just basically trying to get a picture of all the points by plotting, strategic points to get an idea of what it looks like. Okay, the form y equals mx plus b, or f of x equals mx plus b, is called a linear function, which we've talked about. Okay. And its graph is just the graph of the equation y equals mx plus b. Okay. Now remember, m is our slope, and our b is our y-intercept. Okay. Remember, when the slope is 0, we just have y equals some constant. Okay, so that would be y equals b. Okay, that's called a constant function, and all its values are the same number. So basically, we're going to have the same output for every input. Okay, so that would be the function f of x equals b. All its values are the same, and that would be a horizontal line. So here's an example where we have f of x equals 3 or y equals 3. We just have that horizontal line. And remember, the arrows go in both directions, so technically you should be doing this when you graph your lines. Okay, so I do want you to get in the habit of doing that on tests and quizzes and homework. Okay, so, and this would be 2x plus 1. Remember how we talked about graphing? Here's our y-intercept, and the slope is 2, so what we can do is go across 1 and up 2 to get points on there. Okay, across 1, up 2. Okay. So this is the linear function f of x equals 2x plus 1, or y equals 2x plus 1. Okay, so let's look at an example where we're going to sketch some graphs, functions by plotting points. First one we'll look at is f of x equals x squared. Okay, so and the next one is g of x equals x cubed, and that last one will be h of x equals square root of x. So we can start by making a table of values. Now think about like the symmetry that this has. When x is 0, we square it, we get 0, right? But when we go positive 1, we get 1 squared is 1. Negative 1 squared is 1. So we have that symmetry around x equals 0. So we're going to plot points around that 0, going positive and negative. So if I do plus or minus 1/2 for x and I square it, I get 1/4. If I do plus or minus 1 for x, I square it and I get 1. If I do plus or minus 2 for x, I get 4. Plus or minus 3 for x, I get 9. So you can see that, whether our input is positive or negative, we get the same output. Okay. With x cubed, it's a little bit different. It still centers around 0, but when I plug in a negative 1/2 and I cube it, I get minus 1/8. Whereas when I plug in a half and cube it, I get 1/8. Okay, plus 1/8. So 1 cubed is 1, minus 1 cubed is minus 1. That's because we're multiplying 3 times, or an odd number of times, with a negative. 2 cubed is 8, minus 2 cubed is minus 8. So we actually have that symmetry about the origin for x cubed. Okay. And square root of x, we can only use positives, right? So we can look at our perfect squares here, but square root of 0 is 0. Square root of 1 is 1. Square root of 2 is square root of 2. It's 1.414, etc. Square root of 3 is square root of 3, which is 1.732. Square root of 4 is 2. Square root of 5 is square root of 5, which is 2 point something. Okay, so here's what our graphs look like for x squared. Here's our 0, 0, 1, 1, etc. Okay, and then for the negatives, we have positive y's as well. Don't forget the arrows. So the arrows should go here on this one, and here on these. That means they keep going in that direction. This one keeps going, stops at 0, 0, so we don't have the arrow on the left side. Okay, but just plotting those points, we kind of get an idea of what this is x squared, x cubed. We can see the x squared has symmetry across the y-axis. The x cubed has symmetry across the origin, and then this doesn't have symmetry, the square root of x. Now, one thing to note is that if you took this parabola and turned it 90 degrees this way, and then took the bottom part off, it would be the same curve. So this is actually, this half of the curve is right here on the square root. It's the exact same curve. We'll look at that a little more when we talk about inverse functions. Okay, now we're going to talk about piecewise defined functions. So a piecewise defined function is defined by different formulas on different parts of its domain. Okay, so we're going to define it differently for different parts of x. Okay, so we're going to have separate pieces generally when we look at our graph. Okay, so let's look at first at this one. This is a piecewise function where we're saying f of x equals, we're going to see that brace there to show that there's two parts, okay, and we're combining them. So x squared, that's only if x is less than or equal to 1, okay, and then when x is greater than 1, our y or f of x is going to be 2x plus 1. So it's going to be linear when x is greater than 1. It's going to be x squared when x is less than or equal to 1. So we have to pay attention to these because it's not defined everywhere for x squared, only when x is less than or equal to 1, and it's only defined as 2x plus 1 when x is greater than 1. So here's what that graph would look like. Here's our x squared, which we already graphed, right? It's that parabola, but notice that it stops when we get to x equals 1. Okay, so once we get to x equals 1, we're done with it. And then this thing picks up the y equals 2x plus 1, which is a linear equation, slope of 2, intercept of 1. Now it's not going to cross the y-axis here because we're not defining it there. But when x is bigger than 1, we're going to use that line. Okay, so this is our piecewise defined function. Okay, notice we only have the parabola when x is less than or equal to 1, and we only have that line when x is greater than 1. That's why we have an open point there. Close point here because it's defined from x, less than or equal to 1. So here's our definition of the function. Here's what it would look like in the graph. We have two pieces there. Notice there's a gap there. We have two pieces of this function, and we have arrows at the ends here. Okay, let's look at another example of a piecewise function. This greatest integer function is defined by this. You'll see this kind of double, sort of like a double bracket. So double bracket of x means the greatest integer less than or equal to x. Okay, so for 2 it would just be 2, right? But if we're doing that 2.3, it would be 2. Okay, oops. If we do 2.3, it would give us 2. 1.99 would give us 1. Now remember, it's the greatest integer less than or equal to. 0.002 would give us 0. Minus 3.5 would give us minus 4. Remember, we're going smaller, right? And minus 0.5 would give us minus 1. So we call this a step function. Okay. We're not going to look at an example of this, but let's look at the graph of that. Okay, this is kind of a variation on the step function. It's not the exact same one, but it's based on an example. But you see we kind of had these steps like this, and it's open on this end and closed on this end. This is a piecewise defined function because we have different pieces. Okay, if we call it a function continuous, if its graph has no breaks or holes, okay. So we looked at examples 1 and 2, and they were continuous. Examples 4 and 7 are not continuous. Another way to think of that is that continuous is that if you try to draw the graph with a pencil, you don't have to lift your pencil. So if you lift your pencil, it's not continuous. If you have to lift your pencil to draw the rest of the function. Okay. We'll look at, kind of get more in depth with that in calculus in 115. We talk about continuity quite a bit. Okay, let's talk about how we determine whether something is a function. So what curves in our xy plane are graphs of functions? Okay, if you remember when we talked about functions, we said we couldn't have a repeated x, right? And if you have a repeated x, you have vertical lines that line up. Okay, so you can think of this. Let's say this point is 2, 2, and then this point down here is 2 minus 3, right? Notice those points line up vertically. Okay. Sorry, I didn't do that very well. Let's make these red. Okay. So these are our 2 points. They line up vertically. That's a repeated x there. Okay. So if you have 2 points that line up vertically, you have a repeated x, which you can't have for a function. So we can test that on a graph by using what's called our vertical line test. The vertical line test says this. Okay. A curve is a graph of a function if and only if no vertical line intersects the curve more than once. Okay, so if you can draw a vertical line through your curve more than that crosses the curve more than once, it's not a function. Okay. Otherwise, it is. Okay, so let's look at a couple of curves here. Notice this one. No matter how many times we try to draw vertical lines through, we can only cross it once. So that is definitely a function. Okay, but here. Well, here it's okay, but once you get over here, you can cross it more than once. So this is not a function if you're crossing it more than one time. Okay. You don't have to cross it once. You can cross it less, but if you cross it more than once, it's not a function when you're using vertical lines. going through it. Okay, so just kind of summarizing that in words. If each vertical line x equals a, remember that's a vertical line is x equals some number, intersects a curve only once, then exactly one functional value is defined by f of a equals b. Okay. But if a line x equals a intersects the curve twice at a, b, and ac, then you can see we have repeated x, right? Then the curve cannot represent a function because a function cannot assign two different values to a. Okay. And you can see we have a repeated x there, a, b, and ac. Okay. So that would be where our vertical line is crossing the curve at two different points, which it cannot do. So that would not be a function there. Okay. So just doing more vertical lines, we can see that this ellipse shape, that's not a function because we can cross it more than once. This graph here, you can only cross it once with vertical lines, so that's definitely a function. Same with this one. Vertical lines can only cross that once. Okay, so that's a function. This one is not because you can cross it. You can cross it 3 times, right? At some points. Okay, so this one is not a function. This one is a function. This one is a function. This one is not a function. Okay, we're talking about equations that define functions. Basically, we're just saying it's an equation, but we don't have y by itself. So we could have y minus x squared equals 0. It's still a relationship between x and y. Does this equation define y as a function of x? We solve for y, so we get y by itself. And we can see that this does define a function, the y equals x squared. So sometimes you'll see them not, they're kind of implicitly defined. They're not explicitly defined as y equals. They can still be functions, though. You just have to get y by itself. So we could write this thing as f of x equals x squared. So once you get y by itself, you can substitute and write f of x there. Okay, but you have to have y by itself. Okay, let's look at an example here. A couple examples. Does the equation define y as a function of x? So we'll start with y minus x squared equals 2. We solve for y, so we get y by itself, and we said we get y equals x squared plus 2. And that's just taking your x squared curve and shifting it up 2. So that is definitely a function. And we can write it as f of x equals x squared plus 2, okay, for a. Okay, b, however, we have x squared plus y squared equals 4. And when I try to get y by itself, I'm going to subtract x squared on both sides, right? And I take the square root of both sides here. So when I do that, I get y equals plus or minus square root of 4 minus x squared. Notice it's giving us two different y values for a given x. So let's say when x is 0, I get y equals plus or minus square root of 4, which is plus or minus 2, which is not good, right? Because we can't have a repeated y. So this does not define y as a function of x. This is not a function. In fact, what is this thing? This is a circle of center 0, 0 and radius 2, right? So we can see, circles are not functions because they don't pass the vertical line test. So in this case, this does not define a function, right? Even though we can solve for y, but notice it gives us plus or minus. It gives us two different values for each y, where this is, where we can take that square root. Okay, so here's just what we were looking at from the two examples. Here's y minus x squared equals 2, or y equals x squared plus 2. We see we just took our x squared curve and moved it up 2. Okay, and then here's our x squared plus y squared equals 4. Center 0, 0, radius of 2. Okay, and we can see, the parabola passes vertical line test. The circle does not. So this is a function. That's not a function. Okay, so here's some common graphs that we'll see. Our linear functions y equals mx plus b, or f of x equals mx plus b. Here's y equals b, constant function, which is a horizontal line. Standard y equals mx plus b. Here's our y-intercept. Remember, these have arrows on the ends. Okay. Y equals x squared. Okay, or f of x equals x squared. X cubed, symmetry about the origin. X to the 4th. It's kind of a variation on this curve. Okay. X to the 5th. We'll look at that in class. Kind of variation on the x cubed. So these are called power functions. Okay. X to the n. Notice when n is even, we've got that symmetry about the y-axis. So x squared, x to the 4th. And when n is odd, x cubed, x to the 5th, we have that symmetry about the origin. Okay. So we'll look at that in a little more depth in class. Okay. Also worth noting, notice there's no x equals a here, because when you have a horizontal line, when you have a vertical line, it's not a function. It fails a vertical line test. If you put a vertical line right on that line, you're crossing it forever, right? So we don't have a vertical line as a function, just a horizontal line. Okay, and here's some other functions. We're looking at, if we look at square root and fourth root, they kind of look like half that parabola. And it's half the x squared parabola. This is half of the x to the fourth curve. Okay, and it's only positive, right? Because we can't take the fourth root of a negative, or the square root of a negative. For odd roots, cube root and fifth root, we can. The cube root of -8 is -2, right? The fifth root of -32 is -2. So these are going to have values going into the negative as well. Okay, so these are our odd roots. So notice even roots just have half that curve, and then odd roots have that kind of that x cubed curve turned sideways, the x to the fifth curve turned sideways. Symmetry about the origin for the odd roots, okay. And that continues in that pattern. Okay. Reciprocal function. Reciprocal function 1 over x looks like this. 1 over x squared is like a funnel, has symmetry about the y-axis because we're taking x and squaring it. Absolute value function. So absolute value function of x is just a big V there. Okay, and we looked at that greatest integer function, so that's what that looks like. It's that step function there.